This video may make you uncomfortable. That's okay. Because at the end of the day, until you get a real verifiable end product, a button, a bead, an ingot, a coin, you don't have anything. All you have is a piece of paper, a screenshot that just have some numbers on a screen. It's a best guess. It's not real life end product results. And I'm not targeting any specific company in this video. I'm correcting a problem that's widespread across the entire industry. People treating handheld XRF like it's an assay tool for ore and precious metals. And I'm going to stress something up front. In short, handheld XRF is completely useless, and in some cases, an outright scam. This is not about it being 5 or 10 or 20% off. This is about it being completely 100% off. I had people bring me samples alongside handheld XRF results, and it completely defies common sense. And when I put that same material on my proper analytical equipment, the results are completely different. Here's an example. If your XRF tells you that your ore is 20% rhodium, 40% gold, 30% silver, and 10% platinum, that adds up to 100%. And yet you're still holding a rock. Why does it not look like a metal? This problem is so severe that most experienced people in the industry completely dismiss handheld XRF results entirely. The moment you mention XRF, people just turn around. This has led to a terrible reputation with the instrument and a stain in so many mouths. And I get why. Because if your results can be 100% wrong, then what's the point? So today's video, we're going to cover why this happens, why the software output is not the truth, and what you should do instead. I'll show live demonstration, same rock, different spots, different runtimes, so you can see the problem with your own eyes. Now, quick disclaimer, XRF does have legitimate uses, specifically if you use the right instrument. I'm not saying it's completely fake, but it has very specific uses for very specific cases. For example, determining different alloys of aluminum. But these are very specific use cases, not generalized instruments for assaying. You don't believe me? Contact your manufacturer. Speak directly to their engineer, not the salesperson. In order to correctly use your XRF instrument, you need to get an ICP-MS analysis of the ore first to create a calibration. That is the hard truth that no one wants to talk about because it turns an easy scan tool into a difficult and expensive process that defeats its own purpose. Also, another disclaimer, don't do unsafe chemistry. Watch my safety video first. Raw ore is dangerous. So, what is XRF? XRF stands for X-ray fluorescence. Most handheld units use an energy dispersive XRF or EDXRF. There's also a WDXRF, which is a completely different instrument. But here's a simple explanation. Atoms have electrons in shells, and they are at different orbitals. But in short, when an X-ray source excites the atom, an electron will shift and emit a X-ray back at a specific frequencies. Those frequency peaks are the raw signal. And this is the important thing to understand. The raw truth is in the spectrum. The numbers you see on screen is not the raw truth. It is a software interpretation of the spectrum. So remember this one thing. XRF produces a spectrum. Software produces a guess. So here's what I see repeatedly. People send me handheld XRF screenshots claiming insane precious metal contents. Numbers that, if true, would mean the rock is basically a literal treasure chest. Then I run the material on my lab grade analytical equipment, look at the spectrum, look at the chemistry behavior, compare it to what the analysis says it should do, and the results aren't a little bit different. They're a completely different reality. This repeating issue is exactly why experienced miners and metallurgists often completely dismiss handheld XRF claims. The failure mode is not small, it's catastrophic. So let's talk about units, because this is where a lot of people get fooled. Ore grades are usually discussed in grams per ton. 1 ton is 1 million grams. So 1 gram per ton equals to 1 gram in a million grams. That is 1 part per million. So when someone says 5 grams a ton, that's 5 parts per million. 10 grams a ton, that's 10 parts per million. 30 grams a ton, that's 30 parts per million. And yes, I know the difference between a metric and imperial ton. The point still same, stays the same. They're very similar. And the end point is it is an incredibly tiny amount. Tiny. So when someone is scanning a rock and getting ridiculous readings like percent level of anything, understand what that implies. 1% is 10,000 parts per million. That's not normal grade ore. That is basically a metal rich material territory. And yes, it does occur, but you should be able to see the gold nuggets in the sample. And don't confuse it with pyrite, please. And this is one of the reasons handheld XRF readings can become fantasy. People don't understand the scale that they're talking about. They see a number and assumes I'm rich. I get mines constantly bringing me samples and handheld XRF results and saying they have 40% iridium, 20% rhodium, 30% platinum, 10% gold. Add that up and you get 100%. Yet you're holding a rock, not a metal ingot. Situations like this, you have to drop your gold fever and take things for the truth. See what your eyes see and accept reality. Because when I run that same material on my analytical equipment, my proper lab grade Rigaku NEX DE XRF spectrometer, I get a completely different result. Calcium, silicon, aluminum, and other base metal oxides, which are commonly present in rocks. This is over 95% composition of the rocks. How can you have an analytical equipment provide an analysis when it fundamentally cannot see these lighter elements? Yes, that's right. Handheld XRF cannot detect these lighter elements like calcium and silicon, in many cases even aluminum. This gets even further worse when you account for stuff like sulfur, which requires helium gas purge as air physically scatters the X-rays incoming, further causing issues and miscalculations. This is why handheld XRF cannot be used. The instrument cannot measure 95% of what it's made of. How can it be used? Please, please. So here's a blunt statement. XRF does not detect gold like a magical sensor. It records X-ray counts versus energy, like a spectrum, and it tries to fit a model. And the model assumes things like what the matrix is, how the sample absorbs and enhances X-rays, what the overlaps exist, what the calibration library expects, what the geometry and conditions surface looks like. And again, if your equipment cannot detect 95% of the elements, how can it reliably do all those calculations? Instead, what your handheld XRF is runs it through a generic calculation and outputs a number. This number is not a measurement in the way people think. It is an interpretation based off assumptions. Change the assumptions, matrix, surface, distance, moisture, particle size, and the output drastically changes. Each one has a drastic input. I'm not talking about sub percentage differences. I'm talking about an order of 2 to 5 times the actual results amount. That's why I keep saying the truth is the spectrum. The end number is only an interpretation. So let's get into specifics. Here are some major reasons why handheld XRF results on ore can be widely misleading, especially for precious metals. So firstly, sampling or nugget effect, spot size, right? Remember, when you're scanning a tiny spot, ore is not homogeneous. A tiny grain can dominate the reading, or you can miss it entirely. The reading does not represent your tonnage, or represents one tiny area. Look at this rock and look at this side. So if you analyze this side, which has all the metals, that's only a tiny layer where the vein split apart. That doesn't measure this whole mass. So when you go to your investors with the best case scenario and tell them that's your whole tonnage, that's not being honest. Next is surface effects. Simply having a rough surface scatters the incoming and outcoming X-rays. Dust layer skew results, weathering, and coatings completely change the X-ray results because remember, it only analyzes the surface layer. But most importantly, when it's used on these rough, uneven, and contaminated layers, that can destroy reliability. See on screen for what I'm talking about regarding this scattering effect. These are so obvious an issue when you learn about it, yet no one with a handheld XRFs receives this right training to understand this. Nobody understands these effects. Yet I received that training. For me, it is a very important thing to properly prepare the samples, but no one does that. Even deeper at the atomic layer, there's what's called the matrix effect. Two samples can have the same elemental composition, but different mineral matrices, how the atoms are actually rearranged and arranged into a mineral structure. And this is very important because the XRF can output completely different numbers because the matrix changes absorption and enhancements of certain elements. This is a huge reason why generic calibrations fail. The matrix effects have very important effects on the end results. I'll make a dedicated video on this topic and talking about monatomic gold or golds interlaced in a silicate structure or other sulfur and sulfite based minerals. But please, at the end of the day, until you get a final bar material that is properly purchased by a refiner, properly bought by someone else, all you have is speculation and take the reality that your material is not valuable as you may think it is. Next, we have spectral overlaps. Remember, a lot of elemental lines can be close, incredibly close. Peaks can even overlap. This is where false identification typically happens. For example, some peaks are so close to each other that you have one element present, it can cause the software to hallucinate another. Depending on resolution, count statistics, method settings, even with my own analytical equipment, if I have any sort of lead in the sample, it will give a false iridium reading because the peaks are so near each other. We can see this great example. We have 32% lead analyzed. However, it gives a incorrect and false measurement of iridium. This issue applies to all handheld XRFs. Also, any XRF that goes based off what's called energy dispersive XRF. And this is why simply with most of these equipment, they simply have the iridium disabled. This is why being able to analyze the spectrum matters so much. You can see each peak clearly. Simply relying on the numbers doesn't allow you to have the full picture. It doesn't give you all the data you really need. Additionally, your tool itself is very important because again, my X-ray is capable of having multiple different filters and provides me with all this data. That way I can compare silver on a different frequency on a different spectrum versus these lighter elements versus the heavier elements. I can compare it all together with these three different spectrums. Knowing your tool is incredibly important. For example, my machine uses a rhodium X-ray tube. Because of that, its detection limits for rhodium are high, which makes sense because it produces X-rays based off the rhodium. If you use a palladium X-ray tube, then you'll have issues with palladium and so forth. Knowing your instrument is incredibly important. And here's the part that people don't talk about. Handheld XRFs usually come with very specific modes. For example, alloys and very specific aluminum alloys or copper or whatever. Soils for very specific elemental analysis like lead or arsenic. Consumer goods, again, to primarily analyze specifically for lead or other heavy metals that are easy to detect. And then they'll come with mining or geo modes. And then they'll come with mining or geological modes. But here's the reality. For reliable results, you need calibration samples that match your standards, that matches your ore type and matches your matrix. What this means, firstly, you need a representative sample. You need proper preparation. You need verified reference values and calibration built on your specific ore. Even then, like I did the example earlier, results can dramatically change if your ore changes from vein or deposit. This is something that the manufacturer's engineers will tell you themselves that the ore sample must be first sent to a laboratory to obtain a calibration sample. You're not supposed to run the XRF directly on the raw ore. Now, I want to compare a handheld XRF to my lab grade desktop unit. This is called a Rigaku NEX DE. People typically spend $40,000 to $80,000 on a handheld XRF. My desktop system is around that same price range, so it's not an issue of cheap versus expensive. The difference is in capability and workflow. There's a saying that a bad operator blames the equipment, but in this case, it really is both. You need a good equipment and a good operator. There's no way around that. I have other videos on my channel where we actually bought a Chinese desktop XRF equipment. Ended up being a complete scam, a complete failure. But point is, buy the right equipment. This is what I highly recommend. And I want to stress this. I am not sponsored. I am not any affiliated with Rigaku whatsoever. This is my own personal opinion that I strongly recommend people. So, why is my equipment better? Firstly, my run times are a lot longer. You need more counts to stabilize the signal, especially when chasing trace level targets. It can take up to 10 minutes just to do a single analysis. Sometimes people run it for a whole hour or even days on a single sample. But here's what I see constantly. People with a handheld XRF scan a rock for 30 or 60 seconds and stop once they see a number they like.
Wait.
Yet, scan that rock for longer and you'll start seeing dramatically different results. My system can run multiple conditions, filters, and X-ray voltages. That way it can excite specific orbitals and ranges on the atom in order to compare spectrums across various conditions. This multi-conditional approach gives you more information and better control over what you're actually measuring. Instead of just one spectrum, you have multiple different that you can vary. Remember, handheld XRF only gives you one fixed voltage and no filters. Next, because I can analyze the spectrum directly as showed before, I can look for actual peaks where an element should appear. Because again, the spectrum is what the instrument sees. The output number is a software interpretation. Handheld XRF doesn't allow you to see this data to see if there's an actual peak or a conflicting element. So I created a similar profile, analysis profile that I typically use, but all I did was reduce down the seconds to 10. I tried to only have this primarily high filter at the 60 volts. However, it actually only limits the elements able to analyze at that to pretty much the precious metals and like it ended up being like less than 10 elements. So I'm gonna just do everything exactly as the other normal one I do, which is 100 seconds, but I'll just do 10 seconds and compare the results. Okay, so here's a great example. Here I did a 10-minute analysis. Here I did a 10-second analysis. Now remember, I couldn't set the instrument to have the same exact settings as most XRF analytical equipment do, which is an open filter for a full 60 seconds, because that would actually completely eliminate most of these numbers. They're under those parameters. I can only analyze like less than 10 or 12 elements, so yeah, t- for this example, I just kept the exact same settings, the exact same filters, but I only changed the time. Okay, I changed from 10 minutes to 30 seconds. And here's a great example. So we can see here we have a full list of spectrums, right? A full list of various elements that we actually are able to see. And we see examples like palladium. Okay, here we don't even see palladium. It's not even detected. We see a lot more rare earth elements that we simply don't see here. We also see huge differences in the percentages. Okay, upwards around 10% in some aspects. What's also nice is that the equipment will actually provide a statistical error on how accurate the analysis is. And again, we can see how having a longer detection time almost increases the statistical error by around 4 to 5 times, or decreases the statistical error by 4 to 5 times by simply having a longer analysis measurement. So this is why, of course, it's an exponential curve, right? As you go higher or as you go longer, the accuracy decreases. But this is why it's so incredibly important to have long detection times, as you get a completely different analysis simply by a couple of minutes. Alrighty, so I just did 4 different scans on the same exact rock. I did one on this side, I think somewhere right here, then one right here, and then right here. So just throughout the whole rock, just scanned on 4 different sections, and the whole point is to demonstrate how different the results can be. So again, we see mostly the primary composition is somewhat plus or minus the same, right? We see silicon, aluminum, iron based, and then potassium and magnesium, we see it, all the same, right? So overall, the plus minus structure, is the same. But then we actually go down to here and we see completely different results. Like here, for example, we see neodymium, right? This is a very important rare earth element that
a lot of magnets used. Here we don't even see any, if I'm correct. Yep. I don't even see any neodymium. I don't see any right here. I don't. Is there any here? Before I, jump too high. No, I don't. Interestingly, actually, this one has iridium, though this is within the margin error, so um, not worthwhile, but has iridium higher than lead, so that's actually kind of interesting. But point is, you can see how different the analysis is. Here we have cesium, here we don't. Here we have gallium, here we also have gallium, but it's almost twice the difference. So it drastically varies in terms of elemental composition. I'll try to zoom in closer so you can see see the difference. Okay. So huge, 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 huge differences in what is throughout the mixture. Alrighty. So, I mean, I can keep going on, but I mean, it's pretty obvious, right? Just the length of the elemental analysis, and also just a great example is this one right here. Like I have no clue what happened here. You see, it's reading oxygen at like 89%, probably because what could have happened was it wasn't perfect. It was scanning something not exactly at the tip, and it was instead scanning it at, let's say, this valley peak right at the side, and so the X-rays were deflecting. Again, that's a great example of how important the surface preparation is. Like this was completely unintentional, but it shows how much of a difference you have simply by messing up something as simple like that.
Remember, I'll say this again for the third or fifth time. If you can't produce an end product, you don't have any proof. If your analysis defies common sense, treat it as a warning, not as a win. And if a handheld XRF results is your entire argument, understand why people dismiss it. Be safe, be skeptical, and verify anything. Thank you for watching. I'll keep uploading more videos. Stay subscribed.